Section: Introduction. In this section, we discuss fine-tuning as a method for adapting large pre-trained models. We can use direct supervision from a specific task's training set, curated instruction datasets, or human feedback through reinforcement learning. However, fine-tuning can be inefficient, especially for transformer-based large language models, LLMs, due to their high number of parameters, which leads to significant compute and memory demands. For example, fine-tuning models like GPT-3 with 175 billion parameters or Llama with 65 billion parameters typically requires 1,200 gigabytes and 780 gigabytes of GPU memory, respectively. The GPU memory usage during fine-tuning consists of three parts: storing the model parameters, the gradients and optimizer states, and the intermediate activations. Parameter-efficient fine-tuning, PEFT, aims to update only a small number of parameters, which helps reduce the memory needed for gradients and optimizer states. Additionally, quantization techniques use lower precision data types for model parameters, further lowering memory costs. For instance, when fine-tuning the Llama 2-7B model, methods like LoRa and QLORA can reduce memory usage by 12% and 43%, respectively. However, these methods still require caching all intermediate activations during the forward pass to compute gradients in the backward pass. We introduce a memory-efficient fine-tuning method called TOKENTUNE, which significantly cuts down on GPU memory used for storing intermediate activations without compromising model performance on various tasks. TOKENTUNE works by selecting a subset of input tokens and fine-tuning the model based on those tokens. During the backward pass, it approximates gradient computation by backpropagating through the selected tokens, allowing us to cache only a portion of the intermediate activations during the forward pass, thus reducing memory costs. We demonstrate TOKENTUNE's effectiveness with both medium and large language models, such as BERT and Llama, which have hundreds of millions to billions of parameters. Our results indicate that fine-tuning with TOKENTUNE achieves performance comparable to full fine-tuning or other memory-efficient methods while significantly lowering memory usage. Notably, TOKENTUNE can be combined with existing methods for even greater memory savings. For example, when we combine TOKENTUNE with QLORA, we can fine-tune Llama 2-7B using only about one-third of the memory required by QLORA alone. In summary, our contributions include the following. First, TOKENTUNE is the first method we know of that reduces GPU memory usage for fine-tuning through token selection. Second, it can be combined with existing memory-efficient fine-tuning methods for additional memory reduction. Lastly, our extensive experiments show that TOKENTUNE achieves similar accuracy to other memory-efficient methods while using only 21% of the memory required for full fine-tuning. We also explore related work in parameter-efficient fine-tuning, PEFT, which can be categorized into four types. Selective PEFT methods update only a subset of model parameters using strategies like weight masking. Additive PEFT methods introduce a few parameters to the frozen model and fine-tune only those. Reparameterized PEFT methods utilize low-rank transformations, with LoRa being a prominent example that captures updates through low-rank decomposition. Section Summary. In this section, we introduce TOKENTUNE, a novel method for memory-efficient fine-tuning of large language models that reduces GPU memory usage by selecting a subset of input tokens for gradient computation, allowing for significant memory savings without compromising performance. We demonstrate that TOKENTUNE can be effectively combined with existing methods, achieving up to one-third of the memory requirements of traditional fine-tuning while maintaining comparable accuracy. Section: Hybrid PEFT. In this section, we discuss hybrid PEFT methods, which aim to merge various PEFT approaches like adapters, prefix tuning, and LoRa. We have explored the design space for combining these methods, both manually and through automated techniques like neural architecture search. While these PEFT methods enhance parameter efficiency, they can still lead to high memory usage during fine-tuning. Our proposed TOKENTUNE can be integrated with these methods to improve both parameter and memory efficiency, as demonstrated in our experiments. We categorize several techniques to enhance memory efficiency in fine-tuning large language models into 4 groups. Some PEFT methods focus on achieving both memory and parameter efficiency at the same time. For instance, side tuning methods introduce small, learnable networks that operate separately from the main model, allowing for reduced memory needs by only backprop aggregating through these side networks. The reversible model, known as MEFT, eliminates the need to store intermediate activations during the forward pass. LoRa-FA enhances LoRa by freezing certain weights to lower memory usage. Gradient checkpointing helps reduce memory by only saving some intermediate activations during the forward pass and recalculating others during the backward pass. Quantization is a technique that compresses data by using fewer bits to represent numerical values, which decreases memory usage during both fine-tuning and inference. Approximate gradient methods lower memory consumption by using estimated gradients instead of exact ones for weight updates. Some of these methods utilize low-rank factorization to cut down on memory costs, while others, like meso, approximate gradients using only forward passes. We consider TOKENTUNE as an approximate gradient method since its token-selective fine-tuning strategy approximates the full gradient, representing a novel approach to enhancing memory efficiency in fine-tuning. Additionally, TOKENTUNE can complement existing methods, leading to further memory savings. Our research indicates that not all tokens in a sequence are necessary for fine-tuning transformer models. We hypothesize that by limiting backpropagation to a subset of tokens, we can optimize transformers for specific tasks more effectively. This approach allows for more compact learning and adjustments during fine-tuning. In our method, given an input sequence, we associate each token with an embedding and compute hidden states through multiple layers. We randomly select a certain number of positions from the input sequence and organize the hidden states into 2 groups, one for the selected positions and another for the unselected ones. This reordering does not affect computation since the positions are encoded in the hidden states. For the classification task, we aim to assign the correct label to the sequence. We use the average of the hidden states from the selected positions in the last layer as input for a multi-layer perceptron, MLP, which produces a probability distribution over the possible classes. During evaluation, we average all hidden states from the last layer for the MLP input. Section Summary. In this section, we explore hybrid PEFT methods that combine various approaches to enhance parameter and memory efficiency during fine-tuning of large language models, LLMs. We introduce TOKENTUNE, which optimizes memory usage by selectively backprop aggregating through a subset of tokens, allowing for more compact learning while being compatible with existing memory-efficient techniques. Section: Language Modeling Task. In this section, we focus on the language modeling task, where our aim is to learn the probability of a token based on all the tokens that come before it. We train our language model using a standard cross-entropy loss applied to a set of randomly chosen positions. We denote the head that projects the hidden state back into the vocabulary dimension as W_LM. A crucial part of our approach is that we turn off gradient computation for the tokens that are not selected. This means that only the selected tokens contribute to the gradient during the backward pass. We explain our method for dense layers and attention mechanisms in separate subsections. For dense layers, we consider a layer where the output is a function of the input, weights, and bias. When we backpropagate the loss through this layer, we only do so for the selected tokens, ignoring the unselected ones. This allows us to only cache the relevant hidden states for applying the chain rule, rather than the entire activation. Our implementation explicitly separates the hidden states into 2 groups, one for the tokens we want to fine-tune and another for those we do not. The forward pass remains the same as standard fine-tuning, except we disable gradient computation for the unselected tokens using PyTorch's torch.no_grad. For attention layers, we compute attention using concatenated weights for queries, keys, and values. Again, we disable gradient computation for the unselected positions. We outline the steps for the forward pass of a transformer model using our TOKENTUNE algorithm. When applying our method to medium-sized encoders, we note that alternatives like zero-shot learning or prompting often do not perform as well as fine-tuning. Fine-tuning medium-sized language models can provide a better balance of cost and performance compared to larger models or prompt-based methods. These medium-sized models can also serve as components in larger systems. We also observe that GPU memory usage varies significantly based on the number of parameters in the fine-tuned model. For larger models, most memory is used for parameters and optimizer states, while for medium-sized models fine-tuned with large batch sizes, more memory is used for intermediate activations, enhancing the effectiveness of TOKENTUNE. To validate our method's effectiveness, we test it on the GLUE benchmark. We conduct a hyperparameter search and perform cross-validation on the development set, using a learning rate range and specific batch sizes for different dataset sizes. We fine-tune BERT large fully or apply TOKENTUNE, propagating the gradient through a limited number of input positions. Our evaluation on the test set shows that the average GLUE score for TOKENTUNE is comparable to full fine-tuning, confirming our method's effectiveness. We also find that TOKENTUNE performs similarly or better than existing state-of-the-art methods. However, we note that memory-efficient fine-tuning methods, including TOKENTUNE, may slightly underperform compared to full fine-tuning due to their simplified optimization processes. We suggest that certain tasks may be more challenging or sensitive to overfitting, indicating a need for advanced techniques to select parameters or tokens more effectively, as well as potential regularization methods, which we plan to explore in future research. Section Summary. In this section, we describe our TOKENTUNE method for fine-tuning language models by selectively computing gradients only for a subset of tokens, which helps reduce memory usage while maintaining performance. We validate our approach on the GLUE benchmark, showing that TOKENTUNE achieves comparable results to full fine-tuning, although some performance loss is expected due to its memory-efficient nature. Section: Ratio of tuned input positions. In this section, we evaluate the effect of our token-selective fine-tuning method on model performance by examining how the number of frozen input positions influences results. We fine-tune the BERT base model on two GLUE benchmark tasks, MRPC and STSB, using a learning rate of 5 × 10⁻⁻⁵, a batch size of 32, and 4 epochs. We test various values for the number of trained input positions, ranging from 4 to 64. Our findings, illustrated in the accompanying figure, show that performance improves from 84.8 to 88.8 as we increase the number of trained positions. Notably, tuning just 32 positions yields an average performance of 88.4, which is very close to the 88.8 achieved with 64 positions. Our approach outperforms methods that freeze some of the lower layers, which resulted in a 10% drop in performance on the GLUE benchmark when only the 4 bottom layers were tuned. Next, we analyze the GPU memory requirements for fine-tuning models using different methods. We train our BERT base model for 100 steps on the COLA task with various batch sizes and report the peak GPU memory usage. We compare our method with two similar fine-tuning approaches, ladder-side tuning and LoRa. LoRa freezes most model parameters and only trains additional low-rank matrices, while ladder-side tuning freezes parameters but trains a smaller side network using intermediate activations. Our results show that GPU memory usage increases with batch size for all methods, but TOKENTUNE is significantly more memory efficient. For a batch size of 512, it requires only 9,952 megabytes, compared to 23,196 MB for full fine-tuning. All methods aim to minimize GPU memory usage, with LoRa and LST reducing memory for optimizer states and gradients, while our method cuts down on memory for intermediate activations. Interestingly, we can combine these approaches to further decrease memory usage. By integrating TOKENTUNE with LoRa, we reduce memory to 7,682 MB at a batch size of 512, which is only a third of what full fine-tuning requires. We also explore our method's application to larger pre-trained language models. In the context of instruction tuning, we fine-tune the Llama 2-7B model using the Open Platypus dataset, excluding 2 datasets that contain GPT outputs, and focusing on the remaining 9. We conduct all experiments on an NVIDIA H100 GPU, fine-tuning for 1 epoch with a learning rate of 4 × 10⁻⁴ for LoRa and QLORA, and 4 × 10⁻⁵ otherwise. We use a batch size of 1 with 32 gradient accumulation steps, applying adapters to the feed-forward modules of each layer. For few-shot evaluation, we assess our method against other memory-efficient fine-tuning techniques on several benchmarks, including MMLU, ArcEasy and Challenge, HellaSwag, Truthful QA, and Wino Grande. We utilize evaluation scripts from the Language Model Evaluation Harness to measure performance. Our method shows competitive gains, improving the average accuracy of the base Llama 2-7B model from 60.7 to 61.2. The most notable improvements are observed in the Truthful QA and Wino Grande tasks. Additionally, combining TOKENTUNE with LoRa and QLORA further enhances evaluation accuracy compared to using TOKENTUNE alone. Section Summary. In this section, we evaluate our token-selective fine-tuning approach on BERT-base, finding that increasing the number of trained input positions enhances performance, with notable efficiency in GPU memory usage compared to other methods. Additionally, we apply our method to larger models like Llama 2-7B, achieving competitive performance improvements on few-shot benchmarks while maintaining memory efficiency. Section: Ratio of tuned input positions. In this section, we evaluate how the ratio of tuned input positions affects few-shot accuracy, similar to our previous analysis for medium-size encoders. We assess the few-shot accuracy of Llama 2-7B models fine-tuned with TOKENTUNE, varying the ratio of tuned input positions from 10% to 50%. Our findings, shown in the table, indicate that there isn't a strong correlation between few-shot accuracy and the ratio of tuned positions, unlike what we observed earlier. We often achieve the best results when fine-tuning 20% to 30% of input positions. Notably, the average sequence length in these experiments is much longer than in the GLUE benchmark, suggesting that fine-tuning a smaller number of positions can still effectively adapt the model to specific datasets. Next, we analyze the impact of our method on GPU memory usage for fine-tuning large language models. Our figures and tables illustrate how memory usage for Llama 2-7B changes with the number of trained input tokens. For an input sequence of length 2048, we find that our approach can reduce memory usage by up to 28%, dropping from 89 GB to 64 GB when the number of trained positions decreases from 2046 to 256. Importantly, our method can be combined with other memory-saving techniques. When we combine TOKENTUNE with LoRa or QLORA, we see cumulative memory savings. Specifically, combining LoRa with TOKENTUNE results in peak memory usage ranging from 78 GB to 45 GB, depending on the number of tuned positions. Similarly, using QLORA with TOKENTUNE reduces peak memory from 49 GB to 12 GB with a smaller selection ratio. Overall, our results indicate that TOKENTUNE's performance is not highly sensitive to the token selection ratio, while a smaller ratio significantly lowers memory costs. Therefore, we recommend using a 20% to 30% token selection ratio as a default and exploring further improvements in performance and memory usage with even smaller ratios.